Hello, grade 10s. In today's lesson, we are going to complete motion in one dimension. And in this lesson, we are going to be practicing examples. By going through examples, we can really solidify everything that we have learned. Now, what I always tell my students to start with is to make themselves a little grid like this and draw the xt, vt, and at graphs for stationary objects, for constant velocity motion, and for constant acceleration motion. So you would then, for a stationary object, draw an xt graph with one flat line that represents that the object is not moving, which then means that there is zero velocity and there is zero acceleration. For uniform motion, or constant velocity, the position time xt graph is a single gradient line. I like to put a V above that line to remind myself that by working out the gradient of this graph, I can then work out the velocity. The velocity time graph for uniform motion obviously has a constant velocity, so it is a horizontal line. And I like to put an X beneath it to remind me that the area under the VT graph will give me the displacement. And because the velocity is constant, the acceleration is zero. Now, for constant acceleration, we know that we have 4 different types of xt graphs, but this is just there to remind us of general shapes. So I then just draw the simplest one, which is this type of curved graph. And again, I remind myself that based on this curve, using a tangent, I can work out the instantaneous velocity. The velocity time graph for constant acceleration is a single gradient line. The gradient of this graph will provide me with the acceleration, which can then be transferred to the AT graph. There's a constant acceleration, so it's a horizontal line. I also remind myself that the area under the VT graph provides me with a displacement, and that the area under the AT graph provides me with velocity. This is so useful to have up front and to refer back to as you're answering these graph questions. Let's take a look at the first example. First thing we need to do, given such a question, is to identify what type of graph have we been given to work with. In this case, we have an x versus t graph, so it's a position time graph. So the xt graph for the motion of a car is given. Let the direction of the motion be the positive direction. If that is not given to you, you always want to state the positive direction, and we generally state that the direction of the motion should be the positive direction. So you have to answer a whole bunch of questions related to this graph. So firstly, describe the motion of the car in the first 2 seconds, in the next 2 seconds, and in the last 2 seconds. Calculate the velocity of the car in this part of the graph from 4 to 6 seconds. Draw the corresponding velocity time graph for this motion. Calculate the acceleration of the car from 2 to 4 seconds from the VT graph, which we don't have yet. Draw the corresponding AT graph. Calculate the displacement of the car from the VT graph. And note that unless otherwise stated, we assume that this point here where the x and y axes meet is the point of origin. So let's start. So the first thing we need to do is we need to be able to describe motion in words. Now let's take a look from 0 to 2 seconds. This is a position time graph. So you're starting at the origin And for the first 2 seconds, you haven't moved and you are still at the origin. So what that tells us is that the car is stationary or not moving at the origin for 2 seconds. Now let's take a look at the motion from 2 to 4 seconds. Remember that a curved xt graph tells us that there is a constant acceleration. Now, because the curve looks like this, and remember we learned about 4 different types of xt curves in the case of constant acceleration. But in this case, we have a speeding up because we have a less steep gradient to a more steep gradient. So that indicates speeding up, and because we have an upward curve, that means in the positive direction. So we can then state that from 2 to 4 seconds, the car is accelerating, speeding up in the positive direction. So you can either say for the next 2 seconds or from 2 to 4 seconds. And then lastly, if we look at the xt graph from 4 to 6 seconds, we know that a single gradient xt graph represents a constant velocity. So the car is traveling at a constant velocity from 4 to 6 seconds. So I hope that from this, you can see that that summary of graphs that we looked at on the first slide is very, very useful to go back to so that you don't have to think as much and there is less room for confusion and mistakes. B says calculate the velocity of the car from 4 to 6 seconds from the x versus t graph. Now that part of the graph has a single gradient, and remember that from the gradient of an xt graph, we can work out the velocity. So again, this summary over here is so useful. So we now know that we need to calculate the gradient of this graph over here in order to identify the velocity. So we have to lay it out like this. V equals delta x over delta t, which is equal to xf minus xi over tf minus ti. This is necessary. Now we can start substituting numbers. So we're looking at this little right angle triangle over here. The final position is 5 and the initial position over here is 4. The final time is 6 and the initial time is 4. Now, this is a positive gradient, so we're expecting to get a velocity value that is positive, which means that it's in the positive direction or in the direction of the motion. So that gives us 1 divided by 2, which is 0.5 meters per second in the direction of the motion. So based on the xt graph, using this gradient, we can work out the velocity of the car from 4 to 6 seconds. Now we need to draw the corresponding v versus t graph. So let's come back here. So this is our xt graph that we now need to turn into a vt graph. Now, over here, we've got no movement. It's stationary. So we can see that when the xt graph is flat, there's no velocity. So for the first 2 seconds, the velocity will be at 0. Now over here, we've got a curved xt graph, which here we can see that when we have a curved xt graph, the vt graph is a single gradient line. So we're then going to be able to, on the vt graph, provide a single gradient line. And over here we have an xt graph, which has a single gradient. And when the xt graph has a single gradient, the vt graph is flat. So we now have an idea of what our velocity time graph will look like. So here it is. For the first 2 seconds, there is no velocity. From second 2 to second 4, we have a line that indicates that the velocity is increasing. And then from second 4 to second 6, we know we have constant velocity. Now you'll notice that our x-axis does not change. The time intervals remain exactly the same for the motion, but the y-axis is going to be different because these values represent position and this value over here represents velocity. And the only velocity value that we have is the 0.5 meters per second that we calculated based on this gradient. So from 4 to 6 seconds, we know that the velocity y-axis value is 0.5 meters per second. So we only have two y-axis values on this graph, 0 and 0.5. Calculate the acceleration of the car from 2 to 4 seconds from the velocity time graph. Now again, you can go back to that summary of graphs. What we know, what we can see from that is that based on the gradient of a velocity time graph, we can calculate acceleration, and we've got enough information to be able to calculate this gradient. You have to write this out. A equals delta V over delta T, which is VF minus VI over TF minus TI. Now we can look at our final velocity minus initial velocity and our final time minus the initial time. So it's going to be 0.5 minus 0 over 4 minus 2. Note that we have a positive gradient, so we expect a positive answer. And our final answer is 0.25 meters per second squared. And we've already established that in this case, the car is speeding up in the positive direction, which is the direction of the motion. The next question asks us to draw the corresponding acceleration time graph. So this was our original position time graph. Then we managed to draw this velocity time graph. So again, if we come to the summary of graphs, it makes it a lot easier for us. This is the velocity time graph. Now what we know is that when the velocity is 0, the acceleration is also 0. So we're going to have 0 acceleration for the first 2 seconds. We know that when the velocity graph has a gradient, that means a constant acceleration. So from second 2 to second 4, we are going to then have a constant acceleration represented by a horizontal line. And then in the last 2 seconds, we can see a velocity time graph that looks like this one over here. It is flat, so a horizontal line, and that also represents 0 acceleration. So coming back here, we can see that in the first 2 seconds, there's 0 acceleration. From second 2 to second 4, we have a constant acceleration, and that value is 0.25 meters per second squared. We calculated that based on this gradient of the velocity time graph. And then for the last 2 seconds, again, we have 0 acceleration. So again, the x-axis remains identical for the xt, vt, and at graphs. The x-axis does not change. The time remains constant. The y-axis values are different because this represents meters, and this represents meters per second, and this represents meters per second squared. So the values are different. Calculate the displacement of the car from the velocity time graph. Recall that we can calculate displacement based on the area under a velocity time graph. Now, that question specifically asks you to calculate the displacement based on the velocity time graph, but in general, you would just be asked to calculate displacement. And you would have to know and realize that displacement can be calculated based on the area under a velocity time graph. So we're going to work out the area under the VT graph. So from 0 to 2 seconds, there is no area. So the displacement is 0. And the reason that there's no area is because there is no motion. So there's no velocity. So there is no displacement. From 2 to 4 seconds, there is an area under the velocity time graph, but note that it's a triangle. So for a square or a rectangle, we can work out area as length times breadth. For a triangle, we have to halve it. It's half length times breadth. But we don't set it up like that. We have to set it up as x, v, and t in those terms. So in this case, the x represented by this area is equal to half of the velocity times the time. So it will be half of this velocity, which is 0.5 meters per second, times the time, which is 2 seconds. And so in this time interval, the displacement is half a meter. Always, because it is a vector, we have to state the direction, and in this case, it's in the direction of the motion. And finally, from 4 to 6 seconds, we may calculate it as x equals v times t, which is 0.5 times 2, which is 1 meter in the direction of the motion. So now we need to add up all our displacements. All of them happen in the positive direction, so nothing is subtracted. They're all added up. So in total, the displacement was 1.5 meters in the direction of the motion. Let's take a look at the next example. And in this case, we were given a velocity time graph for a truck. We were asked to calculate the distance and the displacement of the truck after 15 seconds, which is the entire duration of the motion that's graphed here. And let the direction of the motion be the positive direction. We always want to state that up front if it hasn't been given to us. Now, this is quite a common question that comes up that tests your understanding between distance and displacement. Based on a velocity time graph, by working out the area under the graph, we may work out the change in position, which is the displacement. What we need to recall is that distance does not take direction into account, but displacement does. So let's start working out the areas under this graph. So from 0 to 5 seconds, x equals half v times t, which is half of 4 times 5, which is 10 meters in the positive direction. We got a positive answer, which means in the positive direction. From 5 to 12 seconds, we have a rectangle, so x equals v times t, which is 4 times 7, which is 28 meters in the positive direction, or the direction of the motion. From 12 to 14 seconds, we have x equals half v times t, which is half of 4 times 2, which is 4 meters in the direction of the motion. Now, let's just note something very important here for a velocity time graph. If we have our graph in the first quadrant, that always means the positive direction. What we have here is an object that starts off stationary at 0 meters per second and it speeds up to 4 meters per second. It then moves at a constant velocity of 4 meters per second, and then it is slowing down from 4 meters per second to 0 meters per second. That is where we got up to in our explanation. But this is all happening in the positive direction because we're in the first quadrant. For the last second, from 14 to 15 seconds, we're in the fourth quadrant. We're going to get a negative answer. You're going to see that the calculation is going to produce a negative answer. What is actually happening here? The velocity of the truck starts at 0 at 14 seconds, and it is speeding up to 2 meters per second. So it is speeding up, but it is speeding up in the negative direction. So let's take a look at the calculation for the last second. It's a triangle over here. We're working out this area over here. So it's half v times t. So it's half of minus 2 times the time, which is 1 second, which gives us an answer of minus 1. But we can't leave a vector as a negative. It means 1 meter in the negative direction, which is in the opposite direction to the direction of the motion. So what we need to do now is calculate the distance and the displacement, keeping in mind that distance does not take direction into account. So for distance, we need to just add up all the lengths that we've traveled. So it's 10 meters plus 28 plus 4 plus 1, which gives us a final answer of 43 meters. For the displacement, which is the change in position from point A to point B in a straight line, we have to take direction into account. So in this case, we're going to say 10 plus 28 plus 4 minus 1. And that gives us an answer of 41 meters. And the fact that this answer is positive means that our displacement happened in the positive direction. This is a very commonly asked question that's actually quite simple to work out if you have the hang of it. Let's take a look at the next question, where we've been presented again with an xt graph that describes the motion of an athlete. Let west be the positive direction. So we know that this motion is taking place in the positive direction. And in this case, west has been defined as the positive direction. We need to calculate the velocity of the athlete in these first 4 seconds, the velocity of the athlete from 4 to 7 seconds, and to describe the motion of the athlete. Now we already understand that by working out the gradient of an x versus t graph, we can work out the velocity. And remember that when there is no gradient, the velocity will naturally be 0. We don't need to prove it by calculation. So let's calculate the velocity of the athlete during the first 4 seconds based on the gradient of the xt graph. So v equals delta x over delta t, which is xf minus xi over tf minus ti, which is 4 minus 0 over 4 minus 0, which gives us an answer of 1 meter per second. We got a positive answer. So that means in the positive direction, which is west. What is the velocity of the athlete from 4 to 7 seconds? We don't need to prove it by calculation. We just need to state that because the gradient of the x versus t graph is 0, the velocity is 0 meters per second. And that's obviously because the object's not moving. It is stationary. And lastly, we need to be able to describe the motion of the athlete. Now, this entire motion is happening in the positive direction, so that's to the west. We need to describe the motion in the first 4 seconds, and then in the last 3 seconds. We know that this line over here represents a constant velocity, and over here we've got no velocity. So what we would say is that from 0 to 4 seconds, the athlete runs west, the positive direction, at a constant velocity of 1 meter per second, which we calculated in the last question, from the origin, which is over here, to 4 meters. So here we have the velocity, and here we have the displacement. Now this is a displacement time graph, but from the displacement time graph, we worked out the velocity. So we have both bits of information. From 4 to 7 seconds, the athlete remains stationary, or the athlete's not moving. And the athlete at that point is standing 4 meters away from the origin in the positive direction, which is to the west. Let's take a look at the next question, which involves a velocity time graph. For the motion represented by the velocity time graph, calculate how far the object has traveled in the first 4 seconds, which is over here, from 4 to 7 seconds, and then from 7 to 10 seconds. And then draw the corresponding position time graph for the motion. Now, because we need the position time graph, and we need to calculate how far the object has traveled in order to provide the position time graph, we know that we need to calculate the area under the graph. So let's start with that. From 0 to 4 seconds, the displacement is half v times t, which is half times 2 times 4, which gives us a displacement of 4 meters in the direction of the motion. Then from 4 to 7 seconds, we have a rectangle, so x equals vt, which is again 2 times the 3 seconds represented here, which gives us 6 meters in the direction of the motion. And then from 7 to 10 seconds, we have a shape that looks like this, which we can break up into a rectangle and a triangle and then add them up. So we've got x equals v times t for this rectangle component. So that's going to be 2, because this over here represents 2, times 1 to 3 seconds, and that gives us 6 meters in the positive direction. But we also need to consider this triangle, which ends at 5 and starts over here at 2. So that means that your velocity, your y-axis, is 3 times the time, which is 3 seconds, and that gives us 4.5 meters. So we need to add up the 6 and the 4.5, and that gives us 10.5 meters in the direction of the motion. Now, in order to draw the corresponding position time graph, here's what we need to consider. What we know is that in the first 4 seconds here, we have a constant change in velocity. So we know that the corresponding x graph for this v graph is going to be a curve. So we're going to have this curve over the first 4 seconds, which is why I drew a line up here so that I know where my curve ends. And I also know that that curve needs to end at 4 meters because we just calculated that this area over here, this displacement, is 4 meters. Now, from second 4 to second 7, well, now the object has traveled an additional 6 meters. So it's already traveled 4 meters away from the origin, and now it is traveling an additional 6 meters, which is why the graph is going to go from 4 meters to 10 meters, because 10 minus 4 equals 6. Another very important thing is that because this is a flat line, this gradient over here is a single gradient. So while from 0 to 4 seconds, we have to represent our graph with a slight curve, from 4 to 7 seconds, we have a straight single gradient line. And finally, from 7 to 10 seconds, we calculated that the displacement covered here is 10.5 meters. Now we're already 10 meters away from the origin. So 10 plus 10.5 takes us to 20.5. And during that time interval, which is 7 to 10 seconds, we have a constant change in velocity, which means a constant acceleration, which means a curved xt graph. So this graph will start off for the first part of the motion as curved. The second part of the motion will be a straight single gradient line. And the third part of the motion is also going to be curved. Note also that if we had to add up all the different displacements, so we've got 4 plus 6 plus 10.5, we get a total displacement of 20.5 meters. So it really does make sense that the motion ends here at 20.5 meters on the xt graph. Lastly, let's take a look at an example where we are presented with an acceleration time graph. And here we have a car traveling east. Let east be the positive direction. We want to calculate the velocity of the car from 0 to 2 seconds, from 2 to 4 seconds, and from 4 to 6 seconds. We want to draw the corresponding velocity time graph. Describe the motion of the car based on the velocity time graph. Now, the motion is the same whether you're dealing with an xt, vt, or at graph. But you will see how the description of the motion from the perspective of velocity time is slightly different from the description of the motion from an acceleration time perspective. So let's take a look. If we come back here to our summary of graphs, we can see that when we have an acceleration, which we have in the first 2 seconds and in the last 2 seconds, it means that there is a constant acceleration and we can work out the velocity of the object based on the area under the acceleration time graph. And we also know that when the acceleration is 0, which is what it is sitting at from 2 to 4 seconds, well, it either means that the object's stationary or that the object is moving at a constant velocity. Now, this might seem a little bit confusing, especially because we need to describe the motion of the graph. So we need to make sense of what is actually happening during the motion. But let's start off by answering the first question. So first, we need to calculate the velocity of the car at the different time intervals. So let's start off by calculating the area under the acceleration time graph, and that will give us the velocity. So the velocity is equal to the area times time, which is 2 times 2, which is 4 meters per second. Now, this acceleration is speeding up in the positive direction. It is a positive value of +2. We know that the car is traveling to the east because we were told that up front as part of the question, and that is key. So because the acceleration is positive, it must mean that the car is speeding up. Now over here, when you provide your final answer for velocity, you only need to state direction. So the velocity of the car is 4 meters per second to the east. But the moment that we start to deal with acceleration, it also makes sense for us to try to identify whether the car is speeding up or slowing down. So in this case, the car is definitely traveling in the positive direction. So because it is a positive acceleration, then it must be speeding up. Now, what is happening from 2 to 4 seconds? We have zero acceleration. Because there's no area under the acceleration time graph, it means either that the velocity is 0 meters per second or that the velocity is constant. So either that there is no velocity or that there is a constant velocity. But it doesn't make sense. Sometimes we have to look at how much our graph, our motion makes sense. It wouldn't make sense that the car would be speeding up at 4 meters per second in the positive direction and then suddenly being stationary at 0 meters per second. So it makes a lot more sense that it has sped up to 4 meters per second and then it has maintained a constant velocity of 4 meters per second. Let's calculate the area under the acceleration time graph from 4 to 6 seconds now to identify the velocity here. So velocity is acceleration times time. Our time is 2, but note that in this case our acceleration is negative. It is -2. Let's note here the negative acceleration. So we know that the acceleration is negative, but we also know that the object is traveling in the positive direction because the question told us that the object is traveling to the east, which is the negative direction. So therefore, by definition, to get a negative acceleration, it must mean that the object is slowing down. Now, this is why we then get a value that is negative for velocity. We have -4, which means that it is slowing down, but still in the positive direction. This is really important information that we need to be able to derive from an acceleration time graph, and I do understand that it is very confusing. So again, because we were told that the car is traveling in the positive direction and the acceleration is negative, then that means that the car is slowing down. The velocity is slowing down, but it is still slowing down in the positive direction. And that is very important information for when we then try to draw our corresponding velocity time graph. So for this part of the graph over here, which resembles this graph over here, we're going to have a velocity time graph with a single gradient. But for this part over here, remember that the object's still traveling in the positive direction. So that velocity time graph will remain in the first quadrant. But because it is a negative velocity and it is slowing down, then for this part of the graph, we are rather going to have a downward gradient. And this part of the graph, like here, is going to be flat because we've already identified that over here, the object just maintains its constant velocity of 4 meters per second. Because we calculated that over here it speeds up to 4 meters per second, and here it has a constant velocity, which would then mean that the object maintains its 4 meters per second before it slows down in the last 2 seconds. So to draw the corresponding velocity time graph, we know that we're going to have a straight single gradient line from 0 to 4 meters per second. The car then travels for the next 2 seconds at a constant velocity of 4 meters per second. And then it is going to slow down over the last 2 seconds, but still in the positive direction. So still in the first quadrant of the graph. Lastly, we need to describe the motion from the perspective of the velocity time graph and then from the perspective of the acceleration time graph. So let's look at the velocity time graph. Again, the motion represented is the same motion, but we would include slightly different values in there. So let's take a look. From the perspective of the velocity time graph, we can say that from 0 to 2 seconds, the car speeds up with a constant increase in velocity from 0 meters per second to 4 meters per second in the positive direction, which is to the east. Then from 2 to 4 seconds, the car travels at a constant velocity of 4 meters per second, still to the east. And from 4 to 6 seconds, the car slows down with a constant decrease in velocity in this case, from 4 meters per second to 6 meters per second, still in the positive direction to the east. And let's describe the motion from the perspective of the acceleration time graph. So from 0 to 2 seconds, the car speeds up from rest with a constant acceleration of 2 meters per second squared to the east. So you can see that the values on the y-axis that we're representing are different for velocity and for acceleration. From 2 to 4 seconds, the car travels at a constant velocity to the east. Now, in this case, the acceleration is 0 meters per second squared. We can add that information in here, but a constant velocity automatically indicates zero acceleration. And here we're describing the motion from the perspective of the acceleration time graph. And lastly, from 4 to 6 seconds, the car slows down to a rest with a constant acceleration of 2 meters per second squared to the east. But because it is negative here, we know that the car is slowing down. I hope that these examples are helpful. There are so many different types of examples, and it is very, very important to practice as many of these graph questions as possible to make them easier to face. They are confusing and they do require a fair amount of practice.